since light has a particle and wave nature, so why not matter has wave nature? So this was considered by de Broglie. He thought that any moving particle, it has a wave nature under certain conditions. So any moving particle, it has a wavelength equal to Planck constant over the momentum of this moving particle. So this is the de Broglie wavelength. Of course, in meters. This is the Planck constant. And this is the momentum of the moving particle. Now, how was this derived? You're not responsible for the derivation, but if you want, you can start by the energy. So we know that the energy is equal to the Planck constant times the frequency. So I can replace the frequency by hc over lambda, okay, which is the speed over lambda, and then I can replace E by the rest mass energy, so it's equal to mc squared. So this is the rest mass energy, it's equal to hc over lambda. Then I can cancel out c from both sides, so I will end up having mc equal to h over lambda. So this would imply that the momentum is equal to h over lambda. So I can write it as lambda, which is the de Broglie wavelength, is equal to h over p. But of course, any moving particle, it has a speed v. So it doesn't have the speed of light, it has a speed v, like the electrons, for example. For example, the speed of electron is considered to be 10 to the power of 5 meters per second. So this equation, it's the wavelength for any moving particle under certain conditions, of course. So then an experiment was done in order to test if this equation or if this theory is correct. So what happened is that they thought, okay, so why we don't do an experiment to check if electron, for example, has wave nature or not. So what they did is that they tried to do diffraction for electron. So if electron, we know previously that if light is passing through an aperture, whenever it passes through this aperture, then diffraction is going to occur, and this is due to the wave nature of light. So if this is going to occur for electrons, then this means that the electrons are matter waves, okay? So they have waves nature. But we know that for the diffraction, in order to occur, the wavelength should be like approximately equal to the aperture size. So what they did is that they used the de Broglie wavelength equation, which is this one, h over mv. So I replaced the momentum by mv, and they replaced, instead of v, the speed of the electron, which is 10 to the power of 5 meters per second. And by the way, this speed, you can find it by accelerating the electron between two capacitors, for example, okay? So if you put it in a potential difference, you can accelerate it, and you can find the kinetic energy from which you can find the speed, for example. And you can replace the mass of the electron, it's in your data booklet, and you can replace by the number, and you can replace the Planck constant by also the number, which is in your data booklet. And you will end up having that the wavelength of the electron is in the size of approximately 10 to the power of minus 10 meters. And you know from the order of magnitudes that this size is the size between the atoms, okay? So this is the size between atoms. So this means that a good aperture for diffracting electrons will be the atoms. So if I brought, let's say, nickel, okay? So let's say these are the atoms of nickel, for example. So as the electron passes through the aperture, which is the size of the distance between the two atoms, so what happened is that on the screen, they noticed that there is diffraction pattern. So there's a region where the intensity of the electron is high, and then minimum, and then maximum, and so on. Okay, so since the electron diffracted, so this means that the electron has a wave nature. Okay, and since this equation was used in order to find the size of the perfect aperture, so this means that this equation is correct. Okay, now sometimes you don't have the speed of the electron. As I told you, sometimes the electron is accelerated in a potential difference. So all what you have to do is the following. So let's say this is the two plates of the capacitors, and let's say that the potential difference across them is V. Okay, so in this case, this terminal should be the positive terminal and this terminal should be the negative terminal. So let's say that the electron is accelerating in this direction. So this means that the kinetic energy gained by the electron is equal to the electrical potential energy lost by the electron, because the electron is approaching the positive terminal, which means that half mv squared is equal to the charge of an electron times the potential difference between the plates of the capacitor. So I'm going to multiply this by 2. It's going to be mv squared equal to 2ev. And then I'm going to multiply both sides by m. So I'll be having m squared v squared equal 2mev. And then this is the momentum squared. So the momentum, it can be written as square root of 2mev. So sometimes if I don't know the speed of the electron, I can write the Broglie wavelength as the Planck constant over the momentum, but I don't have the speed, so I can write it as such. It's square root of 2 times the mass of the electron times the charge of the electron times the potential difference across the terminal of a capacitor. So this is the de Broglie wavelength, but in terms of the potential difference in case the speed is not given. Okay, so this experiment, it has shown you that in the quantum level, particles can have wave nature.